Why do you do anything that you do? What's that?
Because it's needed.
Okay, that would not be, well, probably from their point of view, they'll rationalize it as it's needed.
They might just do it just because they want to do it.
And I think also part of that, also think they'd want to fly, but they're not flying. I was gonna go with, because they can also. They want to do it just to do it. Bragging rights. The official why you would actually get funding other than, hey, I just want to create a new element, would you give me money to do it, is they are testing the theories. If 116 exists, then you should be able to create it in certain circumstances. It should live for a certain It should exist as a wholly intact atom for a certain amount of time, and then it will decay. And so it's basically testing the theories. My suspicion is, I haven't actually met the people who did that stuff. That was nowhere near any of the stuff that I did. But I speculate that deep down is just for the bragging rights. Yeah, I got an element named after me. That kind of thing.
Now, the elements that are not solid colored, what state of matter are they in?
It's quite possible that they do not have enough of them in order to actually declare a state, would be my speculation. So, that, yeah.
Out of curiosity, why are some of the atomic masses in parentheses?
Because they don't have an exact number.
Oh, okay.
I mean, for like 87 down there, I think it's francium. You probably need a whole lot in order to be able to run tests on it. And some of these, and as you get higher up, the less stable they become. Thus, uranium used for breaking apart and creating atomic bombs. So let's talk about why atoms would not be stable. Oh, we got one other thing about what happens if you put two protons near each other? What's going to happen? Besides creating a helium atom.
They're gonna bounce off each other.
I'm not sure bounce is the right word, but yeah, they want to get, they hate each other. Positive charges hate each other, negative charges hate each other. Positive and negative like each other, but they're kept separated. So if I have two protons here in a helium atom, it's got the 2 in the upper right hand corner, so there's 2 protons. On average, there are 4 nucleons, so there's 2 neutrons. But these protons want to get away from each other. So the neutron can act as sort of a buffer. It allows them to be separated, and there's also a force that attracts nucleons to each other. So neutrons, as you get into it, will apply an attraction, as well as keep the positive charges separated. Now it gets harder and harder to do. We start out with no neutrons, on average. Then we have 2 neutrons here. At this point, we have 4 neutrons. We have 5 neutrons. 6 on average, still 6, 7. The number of neutrons increases as you get more and more. We get down to here, and we have, I should have done the one where I could do the math more easily. We got this one right here, and we have 84 protons, and on average, 125 neutrons. So we start out with more protons than neutrons, and then they equal out, and then suddenly we have far more neutrons than we have protons. So I have these extra neutrons which are providing a glue to the nucleus, but also it's separating particles more and more. As the particles get separated more and more, it becomes less stable. And if I've got 4 things in there, yeah, they can stay together, it's pretty hard to break those apart. But now when I've got 209 things inside here, it's much easier to break apart. And so that provides some instability. Make sure there was not something else I wanted to hit before. Oh. All right. So once we have the basic setup of the atom there, the next level of categorization basically is the state of matter, which we've touched on last Wednesday and a little bit today. By categorizing them, it immediately, if we're talking about solids, there are some characteristics that immediately are, that we would want to know about the material. If it's a liquid, there are other potential qualities or quantities, things that we can measure or calculate in order to describe things a little bit better. So when you're talking about all 3 of them, there is something called density that actually works for all of them. So no matter if it's solid, liquid, or gas, we can talk about the density of an object. Pressure is another key term. If we start getting into liquids and gases, we can start talking about things like viscosity. And so jumping all over the place here. So let's just start out with density and pressure. We're not going to do anything with viscosity other than just mention it right there. So let's segue into chapter 11 and density. Now the symbol for density, the one that I use, is the rho. Looks kind of like a T, except a little bit more curl. And it's just mass over volume. So this is mass, this is volume. Hewitt also talks about weight density. This is the only book I've ever seen weight density in. There might be others, but just not something I'm as familiar with other than the fact that Hewitt mentions it. Weight density is weight over volume instead of mass over volume. So let's take a piece of metal here. Oh, here we go. A piece of metal, and just find the density of it easily enough. So first off, volume. We're going to pretend that it's actually a cube right now. The dimensions probably are a little bit off of a cube just because of, you buy from the cheapest. And I need, I have right here. And it is 3.12 centimeters. This 2 right here is estimated. It's a little bit past 3.1, I'm just estimating the 2 there. If we assume it's a cube, how would I find the volume? Flashing back to what, elementary school, whenever you did volumes the first time. Volume of cube. All right, we'll start out with something else. If I have a square here, that's sides S and S, how do you find the area of a square?
You multiply the two sides.
So-
You would multiply both of the sides.
All right, so the area would be, so now I add on another dimension here. How would you find the volume?
You would cube it.
Yeah, so it's just the length cubed. So 3.12 centimeters cubed, which is 27 point something, 28, somewhere there.
$30.37.
Oh. Units?
Centimeters cubed.
Yep. The mass of this, well, you've been finding mass for quite a while here. We got triple beam balances. Probably be faster than turning the electronic one on. And more accurate. It's a little bit unbalanced here. Yeah, we're gonna call that, that's not too far off. Just going for a crude approximation. In the, I guess the lab you'll be doing this week, you'll be doing better measurements than what I'm doing right now. So we're at approximately 85.12 grams. So I have a mass of 85.12 grams. And so what is the density? How would you find it? Yep, but it says right there. So 85.12 grams over 30.37 cubic centimeters. Units?
Grams per centimeters cubed.
Yep, that's a 3 there. Now, if you look in Hewitt, he will not have 2.8 grams per cubic centimeter listed anywhere. He's using SI units, and so he's gonna have kilograms per cubic meter. So the question is, what is the density in, if I want it in kilograms per cubic meter, what is the density? Well, let's do it bit by bit. The length of the side was 3.12 centimeters. How many meters is that?
0.00312.
Move it over 3 places?
Yep.
Anyone else?
Is it 3 or is it 2? 0.0312.
2. Think of centig as in 100 years, that 2 zeros, 2 places. So 0.0312 meters. And so my volume is that cubed.
.0304. Do you want me to round?
0304. That's not right. Point
Oh,
that cubed.
30.3037, right? Now,
It's point times 10 to the negative fifth.
Ah. So what's times 10 to the negative fifth?
It's 3.037 times 10 to the negative fifth.
Ah. You got also?
Yeah, that's fine.
Cubic meters. Not particularly big in cubic meters, but you know, it's small. My mass in kilograms. Well, I had 85.12 grams. So how do we get kilograms?
now it's 3 spaces. Yeah.
0.08512 kilograms. And so my density in kilograms per cubic meter, 0.08512 kilograms over 3.037 times 10 to the negative fifth cubic meters.
802.64. Kilograms per meter.
Yep. And that is closer to what you'll find in the textbook, and I think, somewhere, there we go, table of densities on page 230, and you'll find that aluminum is 2,700. So, if it's not, it's probably not pure aluminum, whatever I put it, so it's over there. Probably not pure aluminum, because I've got some pure aluminum in my office and it's slowly disintegrating. But aluminum, density of aluminum is about 2,700 kilograms per cubic meter. So this comes up with, not really an issue, but a why did I bother doing grams per cubic centimeter when SI units would be kilograms per cubic meter, and the textbook is kilograms per cubic meter. This is indeed the standard international standard. However, the standard was grams per cubic centimeter, and so there are a lot of tables out there, if you go onto the internet, a lot of tables out there still in grams per cubic centimeter. You will see, I still think a majority of them will be in these units right here, just because this is what was sort of established before they decided to come up with the official international standard. And the only difference between the two is a factor of 1,000. So if you ever have this, just move it over 3 places, the decimal point 3 places to the right, and you'll get kilograms per cubic meter. All right, we're about to enter into the serial killer portion of the course. Any questions on this before we?
I'm confused as to how you got 3.037 times 10 to the negative fifth.
If you do, so the length of a side was this.
Okay.
We assumed it was a cube. So it was 0.0312 meters cubed.
Oh,
I think that ends up being that.
okay,
Is that sufficient?
yeah, I'll figure it out from there.
Okay.
What was the difference between the, 2802 and the 2700?
The 2802?
Yeah.
This is what we found experimentally, just from the crude measurements that we did here. And this is what the textbook says the density of aluminum is.
Oh.
Other questions? All right, so here's the serial killer bit. I have 3 meter sticks. So just put one on that edge, one there. So I've got this, so if I extended it out, we'd have 1 square meter right there. It's 1 meter by 1 meter. I now add this in. So basically outlining a cubic meter. So to the edge of the table, to about that far out and over and then up. That's 1 cubic meter right there. So the question is, how many me's would fit inside a 1 cubic meter box? Now the serial killer portion of it is the fact that, assume that I'm pureed. Not this, where there's space being taken up by various body parts. But how many me's, if you liquefied me, would fit into a 1 cubic meter box? So let's start out with guessing. Based on your gut feeling, based on what you see right now and what a cubic meter is over there. And we'll just start out with Joanna. How many me's would fit inside a cubic meter box? Yeah.
I'd say like 10. And I say 10.
Let's say 20.
5?
12.
12.
30.
15.
I'd say 15.
All right, so let's actually figure it out. So first thing we need to do is figure out what is the density of a human being, roughly. So what is the density of people?
In grams?
You're asking, what is my weight in grams?
Is it,
No, it's going to be, excuse me. We can figure it out without knowing that. And just as a side note, weight will never be in grams. That would be mass.
mass?
Yeah, you act like it's not a big deal, but
Your pound, like pounds weight.
yeah. So so let's do that part. My weight in pounds is about 215 pounds. We eventually do need to figure out what mass that is.
Weight to mass, yes.
But asking for density of humans. I assume most of you have gone swimming at some point in your lives.
Is that a constant number?
No, we're doing an approximation here.
Okay.
Any of you ever floated on water? Got one person, only one person, two of you have floated on water. How do you sink once you've, how easy is it to sink?
Pretty easy if you, instead of floating, you change your center when you fall in.
Ah, have you had a different experience?
Yes, it's the same.
Suppose we're not talking about just complete, laying on your back. Is it possible, balled up to float? Maybe our densities are different.
No, you can't.
Huh. I find that when I have a lung full of air, I basically hang out at the top.
When you stop breathing, when you sink, you're gone.
Yeah, or exhale. So a lung full of air, I'm floating at the top, and it's not on your back kind of floating, but part of me is on the surface there. And when I exhale, I sink. So the difference between the density of me and water is that I'm less dense than water. Now I'm more dense than water. So we are approximately the same as the density of water. What is the density of water? So recognize that when you first started doing this, pretty easy communication, you would make densities, you would make any of these things that you are studying equal to 1 in some sort of set of units, just to make it sort of easily translated internationally. So the density of water is 1, just a matter of figuring out the units. And so they did gram per cubic centimeter. That's the density of water, roughly the density of people. Now, the density does depend upon the temperature, and so there's some other factors involved there, but good enough for what we're doing right now. So density, approximately density of human. Since we're dealing with a cubic meter over there, let's get into the SI units. What is the density of water in kilograms per cubic meter? Do I still have that stuff written up? No. You have to rely on your notes. We did it with aluminum. We found it in grams per cubic centimeter and kilograms per cubic meter. By the way.
Oh, 1,000.
Yep, 1,000. So 1,000 kilograms per cubic meter of water. All right, so now I have my weight. What is my weight in newtons? How do I find my weight in newtons? There are at least 4 of you in here who could easily find it.
Wait, sorry, what did you ask me?
How do I find my weight in newtons? How many pounds in a newton, or how many newtons in a pound? For those of you with a book, that's why I picked 4.
Isn't it like 16
Back
point
cover.
something?
Pardon?
Isn't it 16 point something?
No. I'm trying to think where 16 would pop up. It's not going to be 16.
So pounds to newtons,
Yep.
4.448
Newtons per pound
pounds per newton.
is 4.448.
1 pound is 4.448 newtons.
Yeah, okay. So 1 pound 4.448 newtons. So my pounds will cancel out. So I have 215 times 4.448 will tell me my weight in newtons. All right, so that's my weight in newtons. I know that my weight is equal to mg, so I can now find my mass. My mass is going to be 956. Let's see if I can actually write numbers the way I was taught. 956.32 newtons divided by g, 9.798 meters per second squared.
$97.6 here.
Units?
Grams? Grams?
No.
Kilograms.
Yes, kilograms. Yeah, Newton is SI, meters SI, seconds, standard international, so we're in the international standard there. All right, so I know that density is mass divided by volume, and so we know my density roughly, it's roughly 1,000 kilograms per cubic meter. That's going to be equal to my mass, 997.60 kilograms, divided by my volume, or the math problem is 1,000 is equal to 97.6 divided by V. That's the math problem we're working with. So what is V?
Or 76.
Like 0.0976 units?
Centimeters cubed? Wait.
Think about the units of my density here.
Meters cubed.
Yeah, that's cubic meters. Recognize 1 cubic centimeter is, well, actually, that's about 30 cubic centimeters. So if that were cubic centimeters, that would make me incredibly tiny. All right, so my volume is that's the volume of one of me. So the question is, how many will fit inside 1 cubic meter? Well, it's going to be this times the number of